Okay, yeah, so thanks very much for the invitation to be here. This seems like a great little workshop, and thanks to Chris for really setting things off nicely, and in particular queuing up a little bit functional programming, because the first kind of puzzling thing you might be wondering if you don't know much about this is that this is supposed to be a workshop on parallel computing, and I'm going to talk quite a lot about functional programming, mainly in fact about functional programming. And so there is a reason, right? There is a reason. So I'm going to try and explain what functional programming is, why it solves many of the problems of computing, not only problems related to parallel computing, but in particular why it solves many of the problems of parallel computing, and hence the link to this course should hopefully become clear. So it's meant to be a bit interactive, right? So it's meant to be, I'll do a bit of theory or introduce some language, and then you have a go hands-on yourself doing it. Obviously, you don't have to, but if you do have a laptop, then it probably makes sense to kind of boot it up and try and follow along. If you've tried to install something in advance, that would be good. If you haven't, there's still a chance to set up while I'm talking to try and follow along a little bit. Okay, so as you probably know by now, I'm going to kind of introduce FP and then go through 4 languages / libraries that I think are interesting. So Scala, Haskell, JAX, and DEX. So probably today we'll do Scala and we'll look at the other 3 tomorrow. Okay, so they're the languages we're going to look at. So if you can follow along, that would be great, and I'll kind of give you a break and an opportunity to do stuff at the relevant point. Okay, so let's start off with what functional programming is all about. Good. Yeah. So just to say that this is based, and again, if you look at the material, you'll see it's based on a course I actually put together for the Statistical CDT students, the Oxford Imperial CDT. And again, the motivation is very similar to this, right? We all now have parallel computers, but how do we program them? And I started off, much the same way as Chris back in the 80s in the home computer revolution, playing around with the home computers that had either Z80 or 6502 chips in them, and they were nice and easy to program, and I kind of understood how they worked. But even back then, the programming languages were very unsatisfactory for making the most of those machines. And then processors have evolved, computer technology has evolved at an incredibly rapid pace, and the programming languages that people use have really not kept pace at all. So they were pretty terrible back then, but now most of the programming languages that most people use for most things are just utterly terrible and just really hopelessly inadequate for exploiting modern computer technology. So that's really the starting point. And so if you know languages like R, Python, MATLAB, etc., they're just hopelessly slow. Python still isn't even properly multi-threaded. I mean, there's like major things happening in the Python world where the global interpreter lock is going to finally be got rid of in some situations, but in fact that's going to break most of the libraries. So in fact it'll be a slow and painful process, just like the transition from 2 to 3. Right, so they're slow, they're dynamic, they're often not very well multi-threaded, etc. They're just bad languages, all of them. And so then you say, well, okay, they're slow, but what about languages like C, C++, Java, etc.? Yeah, it's true, they're much, much faster. They have some kind of type system, which is good. They're compiled, which means they're faster and more efficient in general. But they're just as hopelessly inadequate for programming on computers as the other languages, right? They're just not the right starting point. So I programmed quite a lot in C back in the day, and I always felt this couldn't possibly be the right way to program a computer. And then I started doing parallel programming in MPI on Linux VWolf clusters, and then that really brought into focus just how horrible it was, because all of the problems you had with serial code just became magnified 1,000 times as soon as you started trying to write parallel code. And it was just clearly the wrong language, the wrong model, not the right way to think about computation in general, but parallel computation in particular. Right, so what's wrong with all of those languages? Well, I'm going to claim that the main problem with all of those languages, well, there are many, but one of the fundamental problems is that they're all fundamentally imperative. Okay, and so that does link very closely with how CPUs actually operate, right? And so for a long time, I think people thought that it was necessary to use a programming language that very closely mimicked how computer processors work in order to get fast, efficient, useful code. This is not true at all. There are wrinkles and caveats, of course, but by and large, you don't need to use a programming language that closely mimics the hardware in order to have efficient code, and it's much easier to get correct, reasonable, easy to reason about code by not doing that. Okay, so massive advances in computer science. We all know about how hardware technology has evolved, but actually we've learned quite a bit about programming languages in all of those intervening decades as well. It's just we've ignored it all by and large, okay? And so functional programming languages are not new at all, but well, let's just say there's been a big resurgence of interest in them in the last decade or so, as people have gradually come to realize that they're a much better fit for programming modern computers, and in particular, doing things concurrently and in parallel, right? There's a subtle distinction between concurrency and parallel, but for doing any kind of concurrent parallel computing, functional languages are just better, and they're just better generally for building big, complicated pieces of software, which of course lots of people want to do. There's a somewhat orthogonal issue that a lot of the languages that are popular with statisticians are dynamically typed languages where you don't declare the types of anything. There's been a swing away from those as well. So that, but at one point in the 80s, that seemed like a good idea, maybe the 90s. But now pretty much everyone's agreed that that was a terrible idea, and that types are really important for writing code that might actually do what you want. Okay, so there's a need for types as well, but that's really kind of an orthogonal issue. Okay, so what is a functional language? Well, functional programming languages are just much closer to mathematical descriptions of algorithms. Okay, they just describe the computation you want to do, as opposed to how to actually do it effectively. Okay, and so they make use of functions, right? Hence the name. Okay, so most computations can be expressed, and are probably best expressed as just a composition of many smaller, simpler functions. Okay, think about most programs. What do they fundamentally do if you ignore the I/O? They compute something. How do they compute it? Well, it's just a mathematical function. Okay, so if you just think in terms of functions, everything works well. But how do you do that? Well, it turns out to be really important to make use of immutability. Okay, so in mathematics, if we say x equals 5, we don't then later say, you know, x equals 6. If x equals 5, then x equals 5, and x equals 5 forever. If we want the concept of something that changes, like I don't know, things in an array, right? Then you have x1, x2, x3, and you carefully label the different incarnations. Okay, and that's what you would do in functional programming, although there are lots of, again, caveats. So data is immutable. You can't change things. So that changes the way you program, because it means you can't have a conventional, say, while loop or for loop, because you can't mutate a counter. You can't have some variable that's mutating the testing for exiting your while loop, etc. So you need to think differently, but it turns out that thinking differently is exactly what leads to kind of composable, testable code that parallelizes more or less transparently. Okay, so it's just easier and better to write code in these functional languages. I realize this is a controversial statement, but it also solves the parallelism problem, as we'll get to in a second. It's also interesting that they really are much closer to the mathematical models of computation. Okay, so if you take a statically typed functional programming language like Haskell or Scala, they're really very closely related to a model of computation known as the simply typed lambda calculus. And if you've ever heard functional programmers ranting and raving, you'll have heard them talking about ideas from category theory, like functors and monads. What's that all about? Well, it turns out that the simply typed lambda calculus is the canonical example, or a canonical example, of something known as a Cartesian closed category. And so we can actually borrow that as well. So it turns out that because you have to think slightly differently when you're writing functional code, there are some things that would be a little bit awkward to do in a functional language if you didn't know about some of these ideas from category theory that make it actually easy to do. Okay, so sometimes we borrow ideas from category theory in order to make it easy to express things that might be otherwise a little bit clunky to express in a functional language. Okay, that's enough for that. So what about parallelism? That's what we're here to talk about this week. Well, as we've just heard, modern computing platforms feature processors with many cores, possibly many processors, possibly GPUs, etc. And so we need to do parallel programming. Okay. Now, if you've ever done any parallel programming, you will know that it's horrible. So why is it horrible? Well, it's really difficult to write bug-free parallel code. So why is that? Well, because there are all kinds of things that can go wrong in a parallel program that we all find very difficult to think about and keep track of. Okay, so in particular, you often have problems where you'll have multiple threads of processors. Doesn't matter which really, where something on one thread needs to know the state of something on some other thread. And there are a million ways that can go wrong, right? Two threads could be changing something at the same time. Two things could be reading and writing at the same time. You could read an old version because by the time it gets to you, it's changed and now you're using the wrong value. You know, there are just a gazillion things that go wrong as soon as you try doing parallel programming. Okay? But they all essentially, or at least a lot of them, when it comes to this correctness issue, okay, revolve around problems associated with shared mutable state. Okay, you have state in different parts of the program that can change over time, and different processors or threads, or green threads, whatever, have a different view of what that mutable state is, or try and change that state simultaneously, or, you know, again, several other bad things that can happen. Okay, but in a functional programming language, you just said we don't have mutable things at all. Okay, so we don't have shared mutable things, and so 90% of the problems of writing correct, kind of simple, reasonable parallel code just disappear. Okay, that doesn't mean it automatically makes parallel programming trivial, right? All the things that Chris was talking about still matter. Things like communication bottlenecks, granularity of tasks, etc. Right? Those things all still matter. Right, but when it comes to writing simple, clean, correct, testable parallel code, right, most of the problems just disappear. Okay? And that is a bit of a revelation when you get your head around it. Okay, yeah, to the extent that it becomes more or less automatic. And so my main kind of thing I want to get across to people is that the best way to do parallel programming is not to do parallel programming. Right? It's to do functional programming and let the compiler, library, language, whatever, take care of the actual parallel computing under the hood without you having to worry about the details. And that's what a lot of these modern languages and frameworks give you the ability to do. All right. So while we're kind of off, I don't want people to get the idea that the only good thing about functional programming is that it solves the parallelism problem. Right, that's kind of missing the point. What functional programming languages solve is the compositionality problem. And it turns out that almost all of the problems to do with computing are about building software in composable, testable ways. Okay, building big bits of program from smaller bits of program that you already know work in a sensible way without things breaking when things get glued together. Right, and most large complex systems fall apart because as soon as you glue enough bits together, things just start working in unpredictable ways. But if you're doing everything with mathematical functions, we know that functions compose, we know we can glue them together, and we know that the pieces work, and we glue them together in the right way, then the glued together pieces will work as well. And it just so happens that actually this solves the parallelism problem as well at the same time, but it solves lots of other problems too. Okay. So we all know about divide and conquer approaches, you know, things like the fast Fourier transform, belief propagation in probabilistic graphical models, etc. This just becomes like the absolute natural way that we build and construct programs in functional languages. Okay, and in particular, because everything's just a function, they're very easy to test. So we can test the pieces of our program, make sure they work. And so it makes it easy to write kind of testably, sort of provably correct code as well. And again, there's this link with category theory, because this is like your mathematical study of associative composition. And we borrow from that as well. Okay, so what does this mean for statistical computing? Well, basically, you've probably heard of MapReduce. So this is a basic functional model for computation. We have a collection of things. We map an operation over that collection of things. Those things that we do are typically pure functions, and so they can all be done in parallel. So that map operation can be done in parallel. We can reduce, again, we can reduce in parallel. Okay, so we can trivially parallelize and distribute these things, and we don't have to write the code that does it, right? The library can contain the code that does this. We just say, I want to map this, I want to reduce this, and the library, language, whatever, can take care of the parallelization. So there are lots of examples, likelihood evaluations for big data, ABC algorithms, SMC weighting and resampling, lots and lots of things that can be expressed as kind of map reduce style operations. And if you can do that, then they parallelize, and you don't really need to worry about how, right? You just say, I want to map this, reduce this, and it's not your problem how to parallelize it. So this is where we get into issues of where something like a Gibbs sampling algorithm is not necessarily very natural in a pure functional setting. Okay, so how do we do that? Well, we can do it in a pure functional setting, but it would be a little bit clumsy and clunky if we didn't know about comonads from category theory. So, but it turns out if you know about comonads from category theory, then a Gibbs sampling algorithm is just a cobind operation on a comonadic data structure, and so Gibbs sampling is trivial as well. Yeah, so this is why we kind of bring in these ideas from category theory, because it just allows us to solve problems, not that we couldn't solve already, but just solve in a very simple, elegant way problems that otherwise might have seemed a bit clumsy. Okay, probabilistic programming languages, again, very natural. We're just composing together Markov kernels to build probabilistic programs. Very, very natural in a functional language. And again, most functional languages kind of have built-in facilities for making that very easy and natural. And automatic differentiation, also a big deal now in modern statistics and machine learning. Well, if you've got a function, we know how to automatically differentiate a function. It's just a chain rule, and we can apply the chain rule to a function very, very easily, naturally. Whereas applying the chain rule to, for loops, while loops, variables are getting mutated as you go through a loop. How do you automatically differentiate through that, right? I know the chain rule. Chain rule is simple and easy. I can implement that. Right. Whereas differentiating through imperative code, I have no idea how to do it. Obviously, people making these libraries have a good guess at how to do it, and sometimes it works, right? But differentiating a function that's a composition of other functions, right? I know how to do that. That's easy, right? So automatic differentiation, very easy in functional languages as well. Okay, so we need our parallel computing kind of constructs. Okay, so MapReduce is a really, really important idea. So we're going to start with that. Monoids, you will hear functional programmers talk about all of the time. Okay, so what is a monoid? Well, if you remember your abstract algebra, even if you didn't do monoids, you probably did at least one of semi-groups or groups. And monoids sort of live in between. Okay, so it's either a semi-group with an identity or a group without an inverse. Okay, so you just got an associative operation that's closed, and you've got an identity as well. Okay, why is that important? Because all kinds of operations parallelize trivially as soon as you have that structure, and that's the only structure you need. Okay, so the trivial example here is we want to add a load of numbers, right? So these might be, say, likelihoods. They might have taken, weeks to compute each of these numbers. We now just want to add up those likelihoods. Okay. Well, how do we do it? Well, we could start at the left-hand end and take 3 and add 1, and then add 2 to the result, and then add 4 to the result. Just walk through the list of numbers one at a time. that would be an order n operation if we took n things. Okay, but we know that we don't have to do that because we know that addition is associative. So we know that actually we could add 3 and 1 together, and we could add 2 and 4 together, and then we could add the results. Okay, but the advantage of that is that the 3 and 1 can be done in parallel with the 2 and 4. Okay, so in fact, what's really going on here is that we're constructing binary tree where we have the sums, the partial sums. Okay, we have the actual numbers as leaves of a binary tree, and the height of this tree is log 2n. So if we have infinitely many processes, which of course we might not in practice, but it's useful kind of concept to think about. If we had infinitely many processes, or at least more processes than data points, then we go from an order n operation to an order log n operation by doing binary tree reduction. Okay, so we can reduce simply by reducing over a binary tree. Now, what properties of addition did we use to do this? Well, the only property of addition we used was associativity. In particular, we didn't use commutativity. We don't need commutativity at all. The only thing we need is associativity. And reducing isn't the only thing we can do. So what's going to be important for Adrian's stuff tomorrow is the idea of a cumulative sum, essentially. So we all know what a cumulative sum is, even if I can't evaluate it very easily. Okay, but there's a cumulative sum. Okay, so that's called a scan operation. Okay, so we start and we do the cumulative sum. Again, all we need is associativity to do this process. Can we do that in parallel? Yes, we can. We just send things back down the tree in the right way and make sure we end up with the right numbers at the bottom. Okay, so that can be done in order log n as well. Okay, so both reduce and scan operations can be done in order log n time on infinite parallel path. Yeah, so that's the kind of scaling you can reasonably expect. Okay, and the only thing we need is associativity. It turns out to be super handy to have a 0 as well, because of course we don't always have things that are, you know, a multiple of a power of 2, and it's sometimes convenient just to shove a 0 in, right? So in general, in programming, we like to have zeros as well. Look, I started with a 0 here. So usually people work with monoids rather than just semi-groups, but you can do this in principle with a semi-group. Often it's more convenient with a monoid. Okay, so that's going to be an important idea later. Okay, so the point is, what this means is if you can express things, or have I said what a map operation is? So we can take that list of numbers and say we can multiply by 2 to get 0, 6, 8, 12, 20, etc. Right? That's an example of a map operation, and clearly that can be done in order 1 time if you've got infinitely many processes. But crucially, it depends on you not mutating any state. Okay, and these computations not relying on any state. So what was really important here is that your map operation only involves mapping a pure function. And this cropped up in Chris's discussion of Python for comprehensions, right? So in some sense, it's not like a regular for loop, because a regular for loop can thread through all kinds of horrible mutual state and all kinds of things can go wrong. But in a for comprehension, you're really only supposed to map a pure function precisely so that it can conceptually, at least, whether it is in practice or not, be done in parallel. And you notice that a lot of this stuff I'm talking about, it's all conceptually be done in parallel. Whether it is or not is actually just now an implementation detail. Yeah, and again, that's one of the ideas. You learn to express your algorithms functionally, and then it's an implementation detail of whether it's run in serial, in parallel on multiple CPUs, or indeed in parallel on GPUs. So that's just really, it can be a runtime decision how you run your code.
I have a question. This might be a very stupid question, but like, there exists operations that can't be written as compositions of single functions?
No, it's not a stupid question at all, right? So it's called the Church-Turing thesis, which is the proof of equivalence of the computational power of a Turing machine, which is very much like an imperative programming language / computer, and in fact, originally the untyped lambda calculus. Okay, and it's not obvious at all, but they have equivalent computation power. Now, that's not to say that every problem is as easy to express in one of them, right? That's not true at all. But they have equivalent computational power. They're both Turing complete. So all of these languages we talk about Turing complete.
Sorry.
Yeah.
What's the extra memory cost of doing this sort of scan operations that we're at?
That's a good question. I wouldn't have thought it is order n. Actually, I would have thought it's less than order n, but I'm not certain off the top of my head.
Well, if you go to the other things, you go to the minus k these steps.
Yeah.
Some of that is so I think your worst case of it.
It's the same as.
Yeah. But so maybe it is an extra cost of order n.
No, I'll talk about it.
Oh, you're talking. Oh, there you go. Excellent. Good. Right. Yeah. So that is, but it does touch on it and an interesting idea that sometimes functional languages do use a little bit more memory than a corresponding imperative solution, but nothing like as much as most people naively think. Okay. Right. So we heard from Chris about HPC and HTP is kind of related. So there's this distinction between, is it really high performance computing or is it high throughput computing? And if it's embarrassingly parallel, then it's clear that it's really high throughput computing. But actually, all of these big map reduce operations, it's a little bit less clear which it is. But one of the frameworks that Chris didn't mention is Apache Spark, and actually that's a library that lots of people use for doing massive big data computations on clusters. And again, it just makes it trivial because you just write your code in terms of map and reduce operations, and you don't care. It could either be just running on your laptop, or it could be running on a gigantic cluster in the cloud. It doesn't matter. Your code is the same, okay? But the library takes care of distributing the data, mapping appropriately the functions, distributing the functions to be mapped first of all, and then mapping them, and then reducing the results back together, etc., and doing this in a sensible way that is reasonably efficient. The runtime, there's all kinds of analysis. Think about the most efficient way of sending data around and distributing stuff, mapping stuff, reducing things back. But all you do is you just say, I want to map this, I want to reduce that, I want to map that, and it takes care of it all for you. Okay, so that's an example of a framework that allows you to write parallel code that distributes over a large cluster of machines, essentially trivial, because you simply say what you want to map, what you want to reduce. You don't worry about the actual details of how the parallelism is computed at all. So this is very, and you don't have to just use this for analyzing big data. It actually works just as well for doing sort of computations that easily distribute as well, because you can map an expensive function over a relatively small data set and have that expensive function distributed as well, right? So you can use it in all sorts of clever ways if you've got real big data problems. But the issue is that the overheads, network overheads, it has to be the kind of problem where the granularity is such that the overheads won't kill you. And so certain kinds of problems lend themselves well to this, but others not so much. Okay, so another thing we've heard a little bit about is the Python library JAX. So interestingly, JAX is a pure functional language embedded inside Python, which most definitely isn't. So it's a little bit of a weird thing, but it's actually quite nice, and it is my preferred of the Python sort of tensor libraries, because it's a pure functional language, and that really makes a lot of sense. And that's the reason why actually lots of people like it. It seems to be a bit faster than PyTorch and TensorFlow on most kinds of operations. It's because it has a nice, simple, elegant programming model that is very well suited to parallel computation, because it's a functional programming model. Okay, so it's really the same idea. So although it's kind of Python code and not Scala code, it looks very similar because it's all about, you know, mapping and reducing and basically just expressing any algorithm that you're interested in terms of some kind of transformation, ideally a lazy transformation of an immutable data structure using pure functions. Okay, so the crucial ideas are transforming with pure functions and a mutable data structure. Okay, the lazy thing is about optimization. If you do it lazily, you can defer the execution, which means the library or runtime has a chance to analyze the pipeline to see what optimizations it can apply before it actually does it. So that's really like an optimization thing rather than a true or false thing. Okay, but it does make things a bit more optimal. Okay. Right, so where are we at? So functional algorithms, you take your algorithm, okay, and instead of writing it in an imperative style, you express it in a functional style, and then those algorithms are very easy for a computer to work with. That's the crucial thing, that an imperative algorithm is actually very difficult for a computer to analyze and process, whereas a functional algorithm is very easy for a computer to analyze and process. It's just a parse tree, basically, and it's just very simple, and you can transform it, you can compile it to run on CPUs in parallel, you can compile it to run on GPUs, you can distribute it over a cluster, you can automatically differentiate it, etc., etc. Okay, it's just much easier to do that with a functional algorithm. And so in many cases, all of these transformations can be done automatically by the library compiler, etc. And so the user doesn't have to worry about the real guts of how to actually get these things to parallelize correctly. Okay. And you just can't reason about imperative code in the same way. Obviously, people try and people do a good job, but you just can't reason about imperative code in the same way. So JAX we're going to come back to tomorrow morning, but there's a huge ecosystem of tools in JAX. I'm particularly interested in Bayesian computation. I know quite a few people here are. So all of the like probabilistic programming languages are like running to change their backend to JAX. Even things like the machine learning neural network libraries like Keras for TensorFlow is now kind of agnostic about its backend. So you can now run Keras models on a JAX backend, and again, it's faster, etc. So kind of there's a lot of kind of movement in the Python sort of tensor ecosystem towards using JAX as a backend. Okay, it's just of all of the frameworks in Python, it's kind of the least bad, put it that way. Okay, so the final language we'll look at tomorrow morning is a new experimental language called JAX. And again, it's experimental, right? So this is coming out of Google Brain. And so, you know, they might cancel tomorrow, right? So I'm not suggesting everybody like bases their entire future career on this language being supported by Google forever, because that's never a very wise thing to do. But it's a very, very interesting language that I think is what future machine learning and computational statistics languages will look like. You know, whether it's this one or not is kind of not the point, but I think it has a lot of features that we will see in future libraries for statistics and machine learning. Okay, so the idea is that JAX, a lot of good ideas there, functional language for messing around with tensors, but it's sitting in Python, which is a terrible host language for this kind of thing. So why not just have a proper language designed from scratch to do this kind of thing well? Well, that's exactly what DEX is. So we'll have a look at that tomorrow. But you could just think of it as being a pure functional, strongly typed, differentiable array processing language that automatically distributes to multi-core GPUs, etc. Okay, so it does all sorts of stuff that JAX does, but it does it in a nice, sensible, pure, typed functional language. Right, that was that. Am I overrunning already? Of course I am. So let's have a quick look at Scala then. Is there a quick question before we start on Scala, maybe?
There's actually in the previous slide about the compilation, the modeling activity more tricks if you want to very functionally. when you write a lot of functional programming functions, you're composing them in a way that makes them slightly interesting to see what's going on in the interaction between functions. So I was always unsure how much the compiler could do to actually optimize the functions when you are writing them together. So you seem to use a lot of function pointers if you're doing it. Think about it as a quant-based framework because of how you do things like carrying and construction functions.
Okay, so pointers are a different thing, and most functional languages won't have pointers. You do have curry and you do have arrows. Okay, so we do use higher order functions a lot in functional programming, but I don't think that can be used as a compiler. I think compilers understand higher order functions pretty well. Well, we can look at some examples. Okay, so why Scala at all? Well, I personally think it's the best general purpose programming language there is. And so, you know, I know lots and lots of programming languages and I just really like this language. It's sort of like a slightly more modern take on Haskell and a slightly more accessible language than Haskell. And it fixes a few little wrinkles of Haskell. So I think it's a really good language and would recommend everybody to use it. It's currently not the best language for GPU programming. So if GPU programming is really your thing, then you're going to want to know about some of these other things as well. But if that's not so much your thing, I really think Scala's a great language. It's not a pure functional language. So you can define variables. So you define those with var, okay? And then you can mutate those, but that's bad. And in any kind of code editor, vars will be colored in red in your code editor because vars are bad, right? So you don't have mutable variables. You have immutable values. So you declare those with val and you say val x equals 5. And then if you try and add one to it, it will give you an error. But you'll notice that I told you already that Scala is a strongly typed functional programming language, and yet there's been no mention of any types anywhere. That's because it has type inference. So there's a very important difference between having a strongly statically typed programming language and having the right types of variables absolutely everywhere. You do have to write types of variables, in particular in the arguments of functions that you define, but you don't have to write them everywhere. Where the type can be inferred by the compiler unambiguously, it will do so. Okay, so I've talked a lot about immutable collections. Okay, so again, this is where some important ideas come in. Okay, we can create a vector like that, and we can say, well, okay, create an updated vector where I change the element of position 2, which is actually the third position in 0 index, to a 7. And what you get back is a new updated vector. Okay, but the old vector is still there. Okay, so this is like how immutable data structures always work. Okay, so you might have questions about that. The obvious question is, aren't you going to end up copying loads of data, right? That's the first thing people ask when they first see immutable data structures. Well, then the answer is no. Okay, because everything is immutable, you don't have to copy, right? That's the key thing that you need to get out of. Because things are immutable, your need to copy stuff defensively has gone away because you know that something isn't going to change under your nose. Okay, right? So you can just point at all of the elements that haven't changed, okay, and just leave them where they are in memory, because you know that nobody's going to change them. Okay, so you don't have to copy everything. And so actually things like this, you might not store linearly in memory. You might store in a binary tree, which might not be cache friendly, but you could. And then you could actually just keep most of the tree and just replace the bit that's changed and leave all the other bits as they are. Okay, so actually different bits of these vectors could be pointing to the same things in memory, but they're conceptually copies of each other. Okay, so if you're using a proper immutable data structure, it won't just copy stuff every time you modify it. It will return you the modified version, but both versions will still exist, and it hasn't involved copying the whole data structure. Okay, so that's a general feature of immutable data structures. Right, so what can we do with them? Well, we can map them and we can reduce them. Sorry.
So
So if I say x equals to 5, and I want to find x plus 1, am I going to have to create, like you said, I seem to get that you don't have to create a new variable containing x plus 1, right? Is that what you're saying?
Yeah, where's the x plus 1?
Well, no, it was just an example. You were talking about.
Oh, right.
Around.
Yeah. Okay, so so there's a difference between, yeah, so this is an immutable data structure where that was an immutable value. Yeah, so the immutable value you can't ever change. Okay?
Yes.
But here you haven't either, right? Because your reference VI will always point to that vector.
Yes.
And you've got a new reference VIU that points to the new vector. So the things that they're pointing to are also immutable.
Okay. So
Yeah.
VI and VIU are two completely different.
Two completely different things conceptually, and conceptually they're copies. But what I'm saying is that doesn't mean that they've been copied.
Okay. And doesn't this use like
No, because I just said they did. It's exactly the point. It doesn't mean they've been copied. Now, in fact, in this particular data structure called vector, there is a little bit of copying because rather than store everything in a binary tree, there are actually little array blocks at the bottom because they're much more cache friendly. Okay, so that gets back to the cache friendly thing, right? But there's minimal copying.
okay. Okay.
Wait, how does this affect like contiguous data then?
Exactly. So this would be a problem if it was implemented naively as a binary tree. It would not be cache friendly. Now, this is actually because processes are designed wrongly, but that is a problem. Thing that I don't want to get. So this whole linear memory model is right. It's really awful, but it's now kind of really hard to get away from it because processes are actually designed with cache systems that assume it, right? But actually, memory isn't a linear model. It's really binary tree, right? Think about how much RAM you have in your computer, right? It's always a power of 2, right? Why is it a power of 2? Because it's actually a binary tree. So your memory is actually a binary tree. So your actual caches should be designed with that in mind, not with linear memory in mind. But that's a tricky problem to solve. But anyway, yeah, and we're showing. Right, so what can we do with collections? We can map them, and when we map them, again, we map with a pure function, and we get back a new collection, okay? And again, this is, in fact, in this case, a different thing. It's obviously pointing to different things in memory because it's got different numbers in it, okay? So there is potentially an overhead there relative to an in-place operation. But again, not as bad as most people imagine. We can fold, reduce, sum, etc. And in principle, all of those things can be done in parallel. Whether they're done in parallel doesn't depend on any of the code here. It just depends on what the collections are, VI. Yeah, so if VI is a vector as it is here, actually this will happen sequentially. But if it was a parallel vector, it would happen in parallel. Okay, so the code, doesn't care whether operations are happening in parallel or not. Okay, so we can write functions in Scala. So here's a log factorial function. And there are multiple ways we could write this. Okay, so the first thing people worry about is what on earth can they do if they don't have for loops or while loops? Well, actually, it's easy. You can create things like this. So say one when and then map it to a double and then log it and then sum them. Okay, so you can do that and that works and you didn't need a for loop anywhere. But there is a problem, which is that it created a collection of things on the heap, which might not be super efficient, so you might not want to do that. But that's fine, so you can just use recursion, okay? So very often you can avoid a for loop or a while loop just by writing a recursive function, okay? So your log factorial, you say, well, if n is 1, I'm going to return 0, otherwise I'm going to return the log of n plus the result of calling this function on n minus 1. And we haven't mutated anything here. N is just different on different parts of the function. That's okay. That's not forbidden. That's a perfectly valid pure functional piece of code. And that works fine, except that it's not what's called tail recursive. So if you call it on a really big argument, it will actually give you a stack overflow, not a heap overflow, right? So this is better than the previous version in the sense that it's not consuming heap. But it's worse than the previous version in that it's consuming stack. Now, stack is much faster than heap. So that will be great as long as you assure you weren't going to blow the stack, but the stack is a more precious resource. And so it's actually quite easy to blow the stack. So actually that's not such a great implementation. But that's okay because you can implement a tail recursive version, which effectively the compiler compiles down to a for loop or a while loop essentially. But that's the bytecode it generates. But you write it as a nice pure function like this. Okay, so we can avoid for loops basically by using recursion or collections in some way. Okay.
Can you just draw the distinction between tail recursion and non-recursion?
Yes. So tail recursion means that you don't do anything with the result of the tail call. So you see here, the final line is simply calling log fact. It then doesn't do anything with it. Where if we go back one, we called log fact and then we did something to it. So we can't actually compile that down to a while loop because we've got to first of all evaluate it and then do something with it. So if you actually write out the execution trace, the execution traces are different, right? Because you've got to get all the way down to the bottom and then come all the way
Yes,
back
that's
to
the
the bottom.
direction.
Yeah, whereas in the tail recursive version, because we're not modifying the result of the tail call, we just compute on the way. Yeah. And we do that by just carrying an accumulator through that allows us to do that. So this one is kind of the one you want to use because it consumes neither stack nor heap, and it solves the problem that we want to solve. Okay, so there's these standard tricks for avoiding for loops that you get the hang of very quickly, and it's really not that big a deal.
Could you just take a moment to explain the distinction between the two? The heap and the stack?
Oh, the heap and the stack.
It's the one you found for me.
Okay, so they're actually both typically in RAM. But one is much faster than the other. Okay, so it's all to do with how quickly you can evaluate, get things in and out of RAM. So Chris was saying you get things in and out of RAM, it's very slow compared to getting things in and out of registers. So the stack is kind of a bit like an extended register that is very quick to push things onto the stack and pulls things off it. That's why it's called the stack. So it's super fast, but it's limited in terms of its availability. Yeah, so it's quicker than getting things in and out of general memory because it's the indexing and everything is much quicker, but it is more limited in terms of resource. Not every language has a stack, right? But most high level languages do.
And the heap is the.
Doesn't make around, usually in every model. Okay, and that's a distinction that maybe isn't so important. So what is important, and this has come up already, we use higher order functions a lot. So map was a higher order function in that you pass a function into it to get something out. And you can also have functions that return functions from them. Yeah. So both of those are called higher order functions. We use those a lot in functional programming. They crop up all the time. And so most functional languages have support for doing stuff with higher order functions. And in particular, if you've got a function with lots of arguments, you can just pass in some of them and get back a function that takes you from the remaining arguments to the return value of the function. Yeah, so that would be an example of a higher order function. So partially applying a function is an example of a higher order function. Okay, and so think languages like Scala have support for this. So you can indicate how you want to query your arguments, how you want to group them. So you say, okay, in principle, this is y equals mx plus c. It has 3 arguments, m, c, and x. But actually, I'm typically going to pass in m and c to get back a linear function, and that's going to now be a function of 1 argument. So we would say we've partially applied the function by supplying m and c to get back a function that takes us from x to the result. Okay, and that's an example of the sort of partial currying. So full currying is where you do the whole stack, which is what happens in Haskell by default. So you apply the first argument, that gets you back a function that sends the rest of the arguments to the result. Then you apply another argument, that gives you back a function that sends the rest of the arguments to the result, etc. So in Haskell by default, everything is fully curried, but Scala kind of has a slightly more pragmatic model where you can curry any way you like, but it has particular support for kind of recommended or expected uses of currying, partial application.
So is this what gives something pure in a sense doing this?
No, not exactly. I mean, you do use exactly this trick for constructing Markov kernels, right? Where you pass in, say, the parameters that you know and get back a function that, yeah. So you do use this inside samplers, whereby you have a function of theta and x, say, and then in some situations you'll know x, so you'll partially apply that and then evaluate it for lots of thetas, or in other situations you'll know theta, so you'll pass that in and you'll get back a function that applies multiple x's to give you a result, right? So partial application does crop up in these kind of sampling problems all the time, but the give sampling thing I don't want to get into, because that's how you kind of iterate through a structure where conceptually you want to sequentially modify each thing in place rather than apply your Markov kernels in parallel. And that is where it would be a little bit clumsy if we didn't have these tricks we knew about from category theory. Okay, so that's Scala in a nutshell. So why don't we have a go at Scala? So has anyone installed Scala? Yeah, quite a few people. Okay, so let's have a go then. It's a Scala crash course. So, oh, no, that's the same thing. Scala hands on. Control D. So if you haven't installed Scala, you can still play with it, right? Because you can just go to this Scalable website and that just allows you to play with Scala in the browser. So if you're just playing around, then you don't want to bother installing Scala, but you just want to try writing a few lines of code. You can do that with this website called Scalable. And you just copy and paste in that code, run it, that's fine. But if you do have Scala installed, you can just run a Scala REPL and start pasting code into the Scala REPL. Yeah, so if you do have it installed, in particular if you've used Corsair to install it, you'll have a nice command line version of Scala called Scala CLI that does lots of clever things. We'll come back to that later. And there are example programs in the repo if you've got the repo checked out, so you can try running those. But there's this nice tool called SVT that allows you to manage bigger Scala projects. Automatically manage dependencies, versions of libraries, versions of compilers, etc. So you don't have any of these nightmarish problems that you have in Python. If you ever use Python with any kind of real work, you're just constantly battling with version dependencies and things not working and requiring different versions of the libraries to the ones you've got installed, etc. Again, most of these problems are solved in sort of the Java ecosystem generally. But in particular in Scala, using tools like SVT to explicitly manage versions and dependencies, etc. So we can just have 5 or 10 minutes to have a go at that. And obviously, if anyone needs a break, feel free at any time. And obviously, I'd take any questions.
I was too interested. And is in. Yes.
Declare functions, you have to declare the types of the argument. And if it's a recursive function, which this is, you also have to declare functions.
Which is that.
Now, if it wasn't a recursive function, you wouldn't have to declare the return type, but it's constantly good practice to do.
Okay. Oh, I see. It's just in the long. Yes. scale check. And people when they pass it in log stuff. It's in my understanding. And that gets stored in memories or
No, so in the first version of the code, which was not tailored person, those values are then stored on the stack, and that was precisely the problem. Because you couldn't evaluate the last one until you evaluated all of them. So all of those ends sit on the stack, and that was exactly the problem. But no, here, this compiles down to the obvious while loop, right? You initialize your accumulator to 0, you then have a while loop that says, if ends one exit, otherwise add that to the accumulator. Right? That's what it compiles down to. By so nothing is being stored ever.
having some trials in my around these people.
Yeah. It does take a while to get it. But I think it's easier to language like Scala than to say diving in with Jacks and not really understanding functional programming, and then you don't really understand what you're allowed to do and what you're not allowed to do, and why it matters whether this is pure or not, and the input messages are really confusing. So I actually think it's much easier to learn a little bit of functional programming from functional programming language, then try and learn something like
Do you have any advice for like those resource for like trying to learn more long term, like something like Scala?
Yeah.
Do you have some suggestion?
Yeah, that's really further. Yeah.
I'm wondering like outside this this.
With Scala, do you have a console, is it now interactive or it's just
Usual.
all levels in the?
No, there's a REPL unit. Obviously, the big project, they've done fine, right? But what you tend to do is you kind of have most stuff in files. Then you want to test a little bit of code interactively, yeah, you can have a hard record. And you can import the code you've written, and test the code that you've written interactively. So it's a good development. Yeah.
So that's probably.
Yeah, that's a great price. Yeah, it's one of those. You know, it's something different. It's like a bomb, where you get
Well, I think everyone's got started with this, so I'm just a bit conscious of time, so maybe you can finish off playing with this a bit later. Maybe we should move on. So what have we got next? Oh yeah, the running example. That won't take very. Okay, so throughout this session today and tomorrow, we're going to have a little running example, and the little running example is going to be gradient-based optimization of a logistic regression Python. So it's sort of everybody's kind of favorite naughty statistics problem. So I'm pretty sure most people in this audience are very familiar with the logistic regression model. So in fact, the details really don't matter. Point is, there's a likelihood function that you can evaluate. And there's one expression for it. And so we're going to try and write a little gradient-based algorithm in all of these different libraries for evaluating this likelihood function. So you see it involves a bunch of like matrix vector operations. And so actually, even in a language that wasn't functional and wasn't designed with parallelism in mind, if you were using a parallelized blast, actually this would parallelize anyway, but it's still going to be useful for illustrating a lot of the basic concepts in these different languages. Okay, and so to do gradient-based optimization, we need a gradient from somewhere. So that could be either obtained by actually differentiating it, as here, or it could be obtained by autodiff. So some of the languages that we're going to look at will autodiff and others won't. So Scala by default doesn't autodiff. There are autodiff libraries in Scala, but by default it doesn't autodiff. It's not a fully differentiable language by default. Okay, so we're going to use that in the Scala example. So what do I need to say about this? Yeah, there's going to be a data set that's going to give us X and Y. We're going to be able to evaluate the likelihood with a formula on the previous slide. We're going to be able to evaluate the gradient of the likelihood with a formula on this slide. And so we could use that to create a simple gradient descent algorithm. Okay, and we'll just use everybody's favorite toy data set, which is this PIMA data set. It's just going to have 200 observations and 7 predictors. So if this is not a big data set, it's not going to parallelize super well, whatever you do, because it's just so small, it's kind of trivial. And so just running it on one decent core is probably fine. But again, it's going to illustrate the principles. Okay, so that's the problem. The data's in the directory. There are algorithms in the directory for solving it as well. What can we look at next? Yeah, well, what we should look at next, I guess, is how to do this in Scala. So where is that? Yeah. Okay, so here's how we would do it in Scala. And yeah, I could run it live and like paste the bits of code in, but there are tools similar to like R Markdown and Cordo and things for Scala, where you can just write these interactive documents. So that's probably the easiest way to do it. So if you would like to, you can follow along by running svt console from the directory containing the build file. That will give you a Scala REPL, and you can copy and paste the commands in one block at a time and just kind of check that it all works. It should all work because this document executed and produced the results, so it should work. So there are a few imports first of all. So the first bit of code is actually not terribly interesting. It's just reading in a CSV file and creating an X matrix and a Y vector. So I'm just going to skip over that because that's really not the point. Okay, so now we've got an X and a Y. So this is where the functional code starts. So how do you write these in a functional language? Well, it's easy. So here we're just using a library called Breeze for Scala, which is numeric library for Scala. And you write it in the way you'd expect. So here, matrix multiplication and matrix vector multiplication is just a star. But if you want an element-wise product, it's star colon star. Okay, so that's explains the top line. Gradient of log likelihood, again, very similar, very straightforward. How are we going to do this gradient descent algorithm, right? That's the thing where you want to use a for loop or a while loop or something. So how are we going to do that?
So it's a good question.
Yeah.
The vector once, did you prepare it in advance? So it's
Yes.
Okay.
Yeah, so there is a function that creates it in Breeze, but I just created it and told it once just as a basis. So yeah, so log likelihood, gradient log likelihood. Yeah, so how are we doing the ascent algorithm? So we're going to create a function called one step that executes one step of this learning algorithm, this gradient ascent algorithm, which is just going to take your current position and add the learning rate times the gradient log likelihood, obviously, right? But you'll notice I've curried that function so that the learning rate is provided, and then that gives us back a function that simply takes the current state and returns the new state. Yeah. So we will at some point supply the learning rate and get back the function that's actually going to do the advance. So that means that our ascend function doesn't actually take that function or doesn't assume that that function exists. It actually expects a function called step, which takes a vector to a vector. Yeah, so you can see it's a higher order function because it expects as one of its arguments a function to be supplied, and that function that it expects to be supplied is a function that maps a double vector to a double vector. Okay, we have an init, we've got a maximum number of iterations, tolerance, etc. And then we're actually going to execute this algorithm by embedding inside the ascend algorithm the actual recursion that's going to do the ascend. Okay, so we'll call that function go. Very often when we embed recursive functions inside of the functions, we call them go. And that function is going to take the current state, your current likelihood, and the iterations that are left. And what's it going to do? It's going to step, evaluate the likelihood of that new step. It's got some kind of convergence criteria. And so if that convergence criteria is met, you're just going to return the current state. Otherwise, you're going to call back this go function again. And you'll notice this is a tail recursive function, because nothing happens to the result of that second recursive call to go, which means the whole thing is tail recursive, which means it won't consume any heap, it won't consume any stack, it won't load. It will just run until the termination criteria is met, and that will be that. So how do we run it? We create an init. We can look at the likelihood at that init. So it's like it was a reasonable guess, but not brilliant. And then we can ascend using our one-step function using a learning rate of 1e minus 6. So remember, the result of calling that will be itself a function that maps a vector to a vector. We pass that function into the ascend function along with our init, and it will give us back the optimum. Okay, and it does. You'll see that the optimum has a much better likelihood than the start. Okay, so that is there. You want to see if you can run that. There are a couple of ways you can run it. So you can find a version that's designed to be run with Scala CLI, or you can run the version that that is an SVT project. Both of those should just run, do the right thing. You can. There are some exercises there, but we're not going to dwell on the exercises today. But if you want to fiddle around with the code, there's some suggestions for how you can fiddle around with the code, see if you can figure out how to make it. Obviously, this isn't the best way to learn the Scala programming language, but it's really just trying to give you a feeling for these functional languages, how they work, and how they solve the parallelism problem. So I'll just give you a couple of minutes in case you want to have a go with that, and then we'll move on.
A question.
Yeah.
Why do you have to hint at the compiler that you have a tail recursion?
Right. So
the factorial example didn't have that, right?
right. So you don't have to. Okay. So the only purpose of the annotation is that there are some failure modes where, in fact, you think it's a tail recursive function, but the compiler disagrees. And the purpose of the annotation is to turn that, what would be a warning, into an error. So if you put the tail recursive annotation on, if it can't compile it down to a while loop, then it throws an error. Whereas if you don't have the annotation on, it will just throw a warning that you obviously might miss, but that might be bad later on. Yeah. So it just turns out, for example, if the function isn't declared final, then you could actually override it later, and then that would break the tail recursive. But you know, there are just funny little side cases that can break what looks like it ought to be tail recursive, but the compiler isn't sure that it is.
So it's kind of your balance check, but for tail recursion.
Yeah.
Okay, and that makes it less efficient.
No, the annotation doesn't change the efficiency of anything. The annotation, yeah. The only thing the annotation does is determine whether or not the compiler throws a warning or an error.
The compiler can know.
So either way, it will give you a working program. The problem is, if you thought it was tail recursive and it wasn't, it might then fail at some point when you try and use it.
I see.
It's only comprehensive, is one of these things that's sometimes better, like
Which,
big tower effects. Like a depends situation. Or is it, typically.
yeah, I'm struggling to imagine the situation I would sort of imagine. There may be some very obscure case where the version there's rather than stats including principles in that sort of situations, but I think that'd be very much unusual.
Thanks. No, that's good, just I see a version.
Okay, well, I'm conscious that we should try and finish by 5, so we should maybe move on. So I've given like a super quick introduction to Scala, but so far I've not really said anything about parallel. Now, in some ways, that's the whole point, right? You shouldn't have to think about parallel. But in that little example I just gave you, if the numerical library is linked to a parallel blast and layback, then it'll run in parallel. If it's linked to a serial blast and layback, it'll run serial, right? It's just kind of simple as that. But you can kind of take control of parallelism in your Scala code. And the easiest way to do that is using something called parallel collections. And if any of you have used JAX at all, they'll be very much kind of reminiscent of JAX arrays. Okay, so that's the kind of picture you should have in your head. So all of the collections that you have in Scala, there are basically parallel versions of them. So if you use those, everything works in parallel. Okay, so let's just see how it works. And again, you really might, in this case, want to paste this code into the record to see to yourself it working, right? I'm going to like do a version that deliberately runs slowly, and you'll see how it runs faster if you do things in parallel. So we're going to just create a little vector with 10 things in it. Okay, so that's not a huge collection, but it's all right. We're going to make it slow anyway. Okay, so what I'm going to do is, yeah, simulate some Gaussian data, and we want to evaluate the likelihood. Okay, so we know that it's mean 0, variance 1, but we'll pretend we don't know the mean is 0. So we can create a log likelihood, And that log likelihood, again, I've curried it, so you kind of pass in the mean and then pass in the x. It doesn't really matter here. And obviously that will evaluate very quickly, okay? But to kind of mimic a more interesting model, we're going to deliberately slow it down, okay? So we're going to deliberately slow it down by making the thread sleep for half a second before returning the likelihood, okay? So our new likelihood function is going to just sleep for half a second and then evaluate the likelihood. So it's mimicking the slow likelihood computation. So you imagine you have a very complicated model with a slow likelihood, okay? Hopefully that makes sense, okay? So every time you try and call that function LL, it will take at least half a second. So if you paste it into your console, you'll see that, okay? Right, so if we just say, well, let's map that with a log likelihood. Say we're interested in the likelihood of 0, okay? We can map it with LL0. Again, remember the function is curried. So LL0 returns a function that will evaluate the likelihood for a given observation. Okay, that's why we curried it that way. So if we map that vector v with that function, we will get a vector of likelihoods. So if we reduce it by summing, we will then get the log likelihood. Okay, so that makes sense. And if that all happens sequentially, which it will by default, that will take at least 5 seconds, right? Because there's 10 likelihood evaluations, each of which takes half a second. So it's going to take at least 5 seconds to evaluate. Okay, if you do it in your record, have a go, you'll see that that is true. Okay, but if you just convert it to a parallel collection, just by calling dot r on it, now v isn't a vector, v is a part vector. And what does that mean? Well, that means that all map and reduce operations are parallelized, as we would hope. Okay, and so that's it. You now do that same code, exactly the same code on the parallel collection, and you'll see that it evaluates, well, basically, if you've got a multi-core laptop, in half a second, right? Because it's gone from basically being an order n to an order 1 operation. So again, if you don't believe me, you just paste it in your record and you see. So all you do is you sort of say, no, I want to work with parallel collections. And then it handles the distributing it, the chunking it, the thinking how many threads it should really use for this, you know, how many threads is optimal, you know, allocating those threads, gathering them up again afterwards. Okay, so there's overhead associated with doing that, right? So it's not automatic that using these parallel collections will be faster. There are some things where it will be, and some where it won't. But if you've got a sensible kind of computation where parallelism would help, then it will help. And it will look after all the details. Okay, so that's kind of cool. So that's basically your quick introduction to parallel programming in Scala. You just make your collections parallel and job's done. Okay, that's kind of interesting. Yeah.
Is there a reason why Scala created the map function around writing?
If you're doing this, if you're doing a Haskell F map, you go F map function
Data.
Yes. Well, actually, so and this is a very common difference between Haskell and Scala. That basically Haskell has, I don't want to say has everything backwards because that's not true. But the Scala syntax is more consistent with object-oriented programming languages. And although I haven't actually told you, this is actually VP dot map. Right? That's actually syntactic sugar for this method call. Yeah. So you can write it either way. And so that's why it's that way. It's because automatically any single argument method call can be converted to infix notation. And again, that's a really nice feature of the language. Right? But, a bit obscure maybe, but yeah, so that's why it's a different way around. And the same with reduce, yeah, it's really dot reduce, yeah. Okay, so cool. So it's as easy as that to get started with parallel computing. Now, sometimes you want a bit more control of that, and so there's an interesting question of conceptually, how do you manage parallel computations in a safe and pure functional web? Okay, how do you do that, right? You know that in C or whatever, you've got to like manually create threads and, you know, join threads and, oh, it's just awful. Okay, what conceptually is the mathematical model that I want to use to encapture a computation that can happen concurrently? Okay, whether it's actually implemented concurrently or not, what is the right conceptual model? And most people seem to think that the right sort of conceptual model is some kind of future or task or IO type model. And I don't have time to explain really what any of those things are, but I can at least give you a clue about what a future is. So there are a bunch of imports, right? So a future is a computation that can, in principle, evaluate concurrently on another thread or some other lightweight thread type thing. But the future returns immediately. Okay, so we said if we call LL, that will take at least half a second to evaluate. Okay, but if we ask for a future of LL, that will return instantly, but it won't return us the value because it doesn't know the value. It just returns us a future that will at some point contain the value. Okay? So what this means is your program doesn't hang waiting for the result. Your program continues, but what you have is not the log likelihood. What you have is the future that at some point in the future will contain the log likelihood. Okay, and it's up to you to decide whether it does, whether it doesn't, what you do with it. Okay, but conceptually, that is the model, right? You wrap your computation that can be evaluated in parallel in a wrapper. It's typically called future or task or IO, and then you can get the result out of that in the future. And that is then the kind of safe way to do it. You don't worry about threads, you don't worry about, you know, locking, you don't worry about anything. You've wrapped up that concurrent operation in a wrapper that you can query safely and do sensible things with. And in fact, you can map them, okay? And you can map them immediately. That returns then another feature. You can obviously wait to extract the value from it, but then that will lock execution, etc. So some kind of future or task is the right way to manage computations that can be evaluated concurrently. Okay, so what you get back is a future. So if we see how we could use this to solve this problem, if we didn't have parallel collections, how might we solve this problem? Well, we just say, okay, rather than mapping with the likelihood that we know is going to take ages, I'm going to map with a function that takes x to a future containing its likelihood. That will return essentially immediately. But then how do we get the values out of it? Well, there are ways to mess around with futures. Like I said, you can map them, where you can do other things with them as well. But crucially, what we've got is not a vector of doubles, which is what we wanted, right? What we've got is a vector of future of doubles. Now, like I said, there are ways you can mess around with these futures. So one thing you can do is you can use an operation called sequence, which will turn that vector of future of doubles into a future of vector of doubles. So that's just a future that contains those vector of doubles. And like I said, there's no problem with you mapping a future. Okay, so we can map that with a reduce operation to get a future of doubles. So now we've got the thing that we want, the log likelihood wrapped in this future. And at this point, we can then say, okay, well, now I've got this thing that I want wrapped in a future. Now I can just block and wait for it if I want, and you can do that. Okay, so we take that's the vector of futures, we sequence it, we map it with a reduce operation, and then we can wait for the result. Again, we'll get the result in about half a second. Now, there are all sorts of things that I've glossed over here, but this is really supposed to be just kind of making you aware of the primitives that exist for thinking about concurrent computations.
So Darren,
Yes.
So the difference between future and what you might call a lazy evaluation. So I could wrap that computation in a function that takes no arguments.
You could.
Yeah. And then at some point in the future, I could call that function and get the result.
Exactly. It is very similar to that.
What's the difference then?
The difference, well, it's a very deep question, it turns out. But the practical difference here is that the future immediately triggers a computation on another thread.
Right.
Okay.
Yeah.
However, what you're describing is in many ways better and that's what I'm gonna get at. You need to trigger the computation at some point, but actually it's better if you're in control when the computation triggers, actually. So, so that's what's going on here. Okay, so as Chris sort of hinted at, there is one potential flaw with this from a pure functional programmer's perspective, which is that the creation of a future has a side effect, and really functional programming is all about avoiding side effects. And here, the side effect is the creation of a thread, potentially some sort of consumption of potentially precious system resources. So that's potentially bad. And so there are all sorts of other ways you can deal with this using other effect systems. So this is what people in functional programming are talking about when they're talking about functional effect systems. They're talking about systems for managing effects such as I/O or concurrent evaluation. And so there are other systems. So for example, CAT's effect with its I/O monad. And actually that doesn't use threads anyway. That uses what's called green threads, which are very lightweight threads, and so they don't take so long to spin up and spin down, etc. So they're much lighter weight anyway. So this is like a very interesting area, but it's way beyond the scope of this course. But if you want to read up on that, you certainly can. But again, just understanding parallel collections is enough to get you started. And if you ever need a bit more than that, then futures will get you most of the rest of the way. So I don't think you need to kind of obsess over, understanding all of these advanced functional effect systems necessarily just to get started with parallel computing. But I think it's good to have this idea of what is the right way conceptually to think about parallel computation. And I think something like a future is the right way to think about it. Right. Is that it for today? Where are we at? Yeah, I think that's a good place to finish for today, and it's more or less bang on time. So, okay. So, yeah, happy to take any questions, but thanks. Any questions?
Yeah, thank you for this. This is really interesting. I'm wondering, so you've talked and you've shown us actually like a lot of like advantages of functional programming languages. So what do you think are the challenges or obstacles that are preventing it from being used like more widely, more commonly, I suppose? One thing I think you mentioned might have been the processor being, for the memory being in like the attached.
Yeah, no, that's definitely not it. So, like I say, there are slight, marginal use cases where the memory consumption of a functional program is a little bit higher than the corresponding comparative program, but that definitely isn't the reason, right? Because there are all kinds of like amazing advantages to functional programming that massively outweigh that. No, the reason is very simple. It's the learning curve of functional. You have to forget about the for loops and while loops and learn to think slightly differently. Than just that is just quite hard. I don't like doing hard things generally, but it's nothing like as hard as everyone thinks, right? You really just need a couple of tricks, right? Like recursion, collections, and a couple of immutable data structures. And actually, it's very natural, and it's particularly natural. This is also ironic for people with a mathematical background, right? Because we think in terms of functions, right? It's actually much closer to the maths, much closer to the way we think and do things, really, right? Imperative algorithms with for loops, that's just not how we think about things mathematically, right? I mean, we've kind of trained ourselves to think about these things in completely the wrong way. But yeah, it does seem to have a little bit of a steeper learning curve than the normal imperative language, but I really think that's the only barrier.
That's a question we've done with barriers on a very practical level in terms of reusability of other people's code. Very clear. You highlighted that's the main barrier. The secondary barrier is that you may want if they're depending on other elements of software that's on different scale.
Oh yeah, absolutely.
So there's a knock-on effect, I suppose.
Yeah.
First point, but where are we in the evolution of the adoption? What's the bottleneck? People getting on and writing some good statistics libraries for functional programming. programming languages.
Yeah, absolutely. So
It's just waiting for that, or?
well, but it has to happen, right? So we've been waiting quite a long time
Yeah.
and it hasn't happened. So something's going to have to make it happen. And it could be that this kind of concurrent computing revolution is the thing that you needed to kick it off, right? It could be that. Yeah, it's just changing, you know, most HPC programs are still using Fortran code that their supervisor wrote, you know, 50 years ago, right? And, you know, it's just really hard to change the way people do this as well. All the kind of reasons we already know.
But the related question, if you don't mind following, the other question about is, there seems to be, from a little bit of experience from trying that, but there appears to be a middle ground where you adopt patterns from functional programming, from the non-functional languages that may support things. So for instance, C++, trying to strongly tied language with some of the management, I think, now with futures and the stuff. Obviously, it doesn't enforce functional programming, but supports it to some extent. But have you ever any feeling about that middle ground? Is it a sensible place to go? Is it a sensible place to train people about that?
Yeah, I understand the attraction of it, but in my experience, it just doesn't really work. So, you know, Java is constantly playing catch up with Scala. But the problem is that all of its default collections are still beautiful, right? And so people just use them, right? And it's the same as C++. Yeah, you don't have to use the chainsaws, but the chainsaws are still there, and so you can still kill yourself with
The immutability bit seems to be the killer in that process. And you understand the template.
But also it just doesn't support everything. So for example, automatic elimination of tail calls, right, isn't in C++, right? So it doesn't actually, so it doesn't have high-bounded types properly, right, which we really need for advanced functional programming. Again, C++, people will say, well, we can sort of fudge it with template meta programming, but you can't really, it doesn't.
Absolutely concept, but yeah, I take.
You know what I mean?
Yeah.
So I think you're just missing a lot of the important tools.
Your recommendation is to be cautious.
Yeah, absolutely.
Yes, we still have time for another question if there are any.
What should understanding category theory and sort of all the things around that help you understand?
So I think it shouldn't stop anyone from learning functional programming, right? You can learn functional programming and get quite a long way without understanding any category theory. But I think learning a bit of category theory is helpful for when you kind of move beyond the beginner phase, the kind of putting it all in perspective, actually understanding why all of these things work the way that they do, and understanding how you can use a few tricks like monads and comonads to solve some important practical problems, right? It's not just theories for theory's sake, right? They help you to solve important practical problems. So I don't think you should wait until you're an expert in category theory before you start functional programming. Hell, I'm still most definitely not an expert in category theory, right? But once you get into functional programming, you start to actually see why category theory is relevant and helpful.
It's because it inspires the patterns.
Yeah, it's all about patterns, right?
Yeah.
And you know, programming is all about patterns.
All right, so I will say that we close it here today. So thanks everyone for joining. Thanks Darren, thanks Chris for speaking. We'll start again tomorrow at 9 and let's take it again then.